Hey everyone. So in this video, I like to do some general review about inverse functions and use this to then talk about the inverse sine function. And so let's just start by discussing functions in general first. So a function takes an input and it returns a corresponding output. And so if I have the function f of x is equal to 5 plus 15x, maybe just to give this function a little bit more meaning, let's say that the inputs here that represents the amount of time a person has worked. And the outputs of this function gives us the amount of money this person has earned. And then we can take this function and I can plug in some value like 3, an input of 3, and we can compute the output. We would take 5 plus 15 times that input. Let me be consistent with my colors here, 15 times 3. And this would give us 5 plus 45, which would come out to 50. And so the idea here is that f of our input, 3, gives us an output of 50. And using the meaning behind the input and the output of this function, tells us that when this particular person works 3 hours, they earned $50. And so when it comes to inverse functions, well, an inverse function sort of takes this input-output relationship and it sort of reverses it. So here, for an inverse function, it's another function which reverses or swaps the roles of the inputs and the outputs of our original function. And so here, give me a moment to talk about what this means, but before we say that, let me also introduce some notation. So, an inverse function, it's this new function that reverses the roles of the inputs and outputs of some original function. And so if this original function is given the name f of x, then the inverse function we usually label with this sort of -1 in the top right corner of the original function. We call this f inverse of x. And so what do I mean by this inverse function swaps the roles or reverses the roles of the inputs and outputs of our original function? Well, the idea is that if f takes an input of 3 to an output of 50, whatever this inverse function is, it's going to do the reverse of that. It's going to take an input of 50, the output of our original function, and it should take that to an output of 3, the input of our original function. And so, in this case, I'm not going to really dig into how I come up with this function, and that's not really a main topic of this course, but for this particular function, the inverse function is x minus 5 all over 15. And so, the main idea of this inverse function is that it's going to, its inputs are the outputs of our original function, and its outputs are the inputs of our original function. And so, we had some meaning for our inputs and outputs of our original function earlier. Well, now the inputs of our inverse function, they're going to be the earnings in dollars. And the outputs of this inverse function, well, they're going to be the amount of time worked in hours. Right, so earlier we saw that when this person worked 3 hours, they earned $50, and this inverse function says, well, hey, if you input $50 into this inverse function, it's going to tell us the number of hours this person worked, and in this case that's 3. And so something I should also mention about the notation that we introduced a moment ago, that's easy to get confused with, but I just like to emphasize is that is not the case, is that here, when we think about this -1 in the top right corner of, let's say, a number like 3, well, then this tells us 1 over 3, right? This is a negative exponent, and it tells us to take the reciprocal of this quantity. But here, when we write something like f inverse of x, right, this is just notation or a name for the inverse function to f. This is not 1 over f of x. This is not us taking the reciprocal of f of x, and so here this is just a name for the inverse function. If we wanted to write this using that -1, we would have to write something like f of x, and then in parentheses, outside of that, we would have -1 in the exponent of this expression here. So, these are some very slightly different notations for some slightly different ideas, but I just want to emphasize here that this is just a notation for the inverse function to our f function. So something that is very relevant to inverse trigonometric functions is that not every function has an inverse function. So let's take a look at this function f of x is equal to x squared. And let's say we input a value of 2 into this function. Well, here, squaring 2 gives us 4. And notice that if we take that same function and we input -2, we also get an output of 4. And so this poses a problem for when we try and define an inverse to this function f of x is equal to x squared. Right, the idea is that an inverse function reverses the roles of inputs and outputs, and so plugging in, let's say, 4 into some sort of inverse function to this f of x is equal to x squared, there's sort of two possibilities for what our output to this function could be. Right? If f takes 2 to 4 and f takes -2 to 4, and our inverse function reverses this, well, it would make sense to say that f inverse of 4 would be 2, but it also makes sense to say that f inverse of 4 would be -2. And so here, this is not a function, right? So a function takes an input to one specific output, and that's not the case here. This is not a function. And so the fact that we got 4 as an output twice from this function is making it so that this function does not have an inverse function. And so graphically speaking, the fact that this function has 2 points that lie horizontal to one another that have the same outputs makes it so that we don't have an inverse function. Right? If we were to ask what's the inverse of this function applied to 4, it would give us 2 or -2, and then that's not a function. And so here what we're really saying is that the fact that these 2 points are horizontal to one another or fail the horizontal line test tell us that there's no inverse function to f of x is equal to x squared as it is. Another language that people use for this is they say that this function f of x is equal to x squared is not one-to-one, and therefore does not have an inverse function. Okay, so there's no inverse function to the entire function f of x is equal to x squared because there are 2 points that lie horizontal to one another and many different points on the graph. But one thing we can do to define an inverse function, not for the whole function f of x is equal to x squared, but for a portion of our function. If we were really stubborn and we want an inverse function, and we accept the fact that we can't define an inverse function to the whole part, we can define an inverse function to just this part. Right? If we look just on the right side of this function f of x is equal to x squared and ignore the left half completely, then this part of the graph is one-to-one. It does pass the horizontal line test. Right? The idea is that if we sort of kind of forget for a moment about the left side of the graph, we don't run into this issue, and we don't run into this issue. And so we can do that. We can define inverse functions for a portion of the graph that does pass the horizontal line test. And so here, in this case, if f of x is equal to x squared, and we're just looking at x is greater than 0, only looking at x values for this function that are greater than 0, then all of a sudden our graph does pass the horizontal line test, and the inverse to this function would be f of x is equal to x squared. Oh, sorry, not x squared, the square root of x. Right, so this is an inverse to our function only on the right side of this graph. And so notice that if I take my f function, f of x is equal to x squared, and I plug in, let's say, 5. Then here, squaring that gives us an output value of 25. And this inverse function, an inverse function should reverse this and take 25 back to 5, and that's what the square root of x does. Right, so f inverse of x, if we were to plug in 25 into this function, well, the square root of 25 would bring us back to 5. And this would be true for all values we plug into our function that are greater than 0. So notice, though, that f of x, or f inverse of x, is equal to the square root of x. This is only the inverse for x is greater than or equal to 0. It's only the inverse to our original function for x is greater than or equal to 0. Notice it does not undo the function when we try to plug in a negative value into our input. Let's say I plugged in -3 into our function f. Well, it's going to square -3 and give us an output of 9. And if the square root of x was truly an inverse function to the entire f of x is equal to x squared function, it should reverse this and bring us back to -3. But that's not the case here, right? If I take the square root of 9, what we get is +3. And that's not the same as our original input. And so here we can clearly see that the square root of x is not an inverse function for when we have x values less than or equal to 0. So let's apply these ideas to our function y is equal to sine of x. And when we started this video, we had some function whose inputs and outputs had meaning. Right? Our original function that we started with, the input represented the number of hours that person worked, and the outputs represented the earnings that that person made. And when we looked at the inverse function to that particular function, it reversed the roles of the x, or the inputs and the outputs, and this included their meanings as well. So the inputs to our inverse function, well, those were the earnings, and when we look at the outputs of that inverse function, well, those became the numbers of hours worked. And so that's going to be the same when we try and define an inverse function to the sine function. And so for our sine function, the inputs have always represented angles. And this is the case for all of our trigonometric functions, that we're plugging in angles into them as their inputs. And the outputs of this sine function, well, we saw that we can interpret them as the y coordinates on the unit circle. And another way we can interpret them, though this will appear slightly less frequently, but it's still valid, we could interpret them as the ratio opposite over hypotenuse. And so, maybe for an example, if we look at sine of pi over 6, well, this is going to look at the angle pi over 6, or 30 degrees, and it's going to give us the y coordinate of this point on the unit circle. That's 1/2 in this case. Right? So pi over 6, an angle of pi over 6, the output to our sine function is the y coordinate on the unit circle. It's 1/2. And so if we try and define an inverse function to the sine function, if we started looking at something like y is equal to sine inverse of x, if we just even try to begin defining this, the idea is that the meaning of the inputs and the outputs should be reversed here. So here, the input to our sine inverse function, well, this should be the outputs of our original sine function. These should represent y coordinates on the unit circle, or ratios, opposite over hypotenuse. And then the outputs of this inverse function, well, they should be the inputs of our original function. We should get out angles. Right, so the idea is that we would expect, if we were to take sine inverse of 1/2, we would expect to get pi over 6 from our previous computation. Right, but the problem actually is that this isn't the only input that leads to an output of 1/2. So just like our f of x is equal to x squared function, it did not pass the horizontal line test. Our sine function actually doesn't pass the horizontal line test as well. Right, so if I look at the output value of 1/2 on the graph of our sine function, we see that it crosses the graph, this horizontal line of y is equal to 1/2. It crosses the graph of our sine function twice in this part of the graph. Actually, it crosses it infinitely many times if we look really far out to the left and really far out to the right. There are many different angles that give us an output of 1/2 for our sine function. Right? Any angle that's coterminal with pi over 6, and any angle that's actually coterminal with 5 pi over 6, right? If we look at the picture above, if we look at an angle of 5 pi over 6, we would also get the same result of an output of 1/2 from the sine function. And so here, if we look at sine inverse of 1/2, it would also be reasonable to say, well, maybe this is not just pi over 6, but maybe it's 5 pi over 6, or 13 pi over 6. And the list would go on and on and on. And so the idea is that we're going to do the same thing as what we did to our y is equal to x squared function, is that we're not going to try and define an inverse function to the whole sine function, because that wouldn't make sense. And the result wouldn't be a function. Right? We wouldn't get one output for this input of 1/2. And so here we can just try and restrict our graph, our function y is equal to sine of x, to a part of it that does pass the horizontal line test. And that's what we're going to give an inverse function. That's what we're going to define an inverse function for. So sine inverse of x is not going to be an inverse to the entire function, but it's just going to be an inverse to a part of our sine function that does pass the horizontal line test. And so the part of our graph that we do define an inverse function for is this part of the graph. So if we just cut out or look at this part of the graph of y is equal to sine of x, this part that goes from negative pi over 2 to pi over 2, well, this is a part of the graph that is one-to-one. It is going to pass the horizontal line test, and it's not going to make the inverse function fail to be a function. And so let me write that down. So y is equal to sine inverse of x is the inverse function to y is equal to sine of x only on the interval of angles between negative pi over 2 to pi over 2. And so what I mean by this is that our sine inverse function only undoes the sine function when we're looking at angles plugged into our sine function between negative pi over 2 to pi over 2. Okay, so how do we evaluate this sine inverse function? The idea is that it's the inputs of the sine inverse function. They're going to be y coordinates on the unit circle, right? These are going to be the outputs of our original sine function, but they're only going to give us angles between negative pi over 2 and pi over 2. And so if we use our unit circle to try and evaluate sine inverse, what we're really saying is that here, for example, if I'm trying to evaluate sine inverse of negative square root of 3 over 2, this is saying the y coordinate on the unit circle is negative square root of 3 over 2. And what we're asking for is the angle, the corresponding angle that gives us this y coordinate of negative square root of 3 over 2. But we're only asking for angles between negative pi over 2 and pi over 2. And so there are many different angles that give us this output of negative square root of 3 over 2, but we're specifically looking for this angle that falls in this interval here. So here in this picture, sine inverse of negative square root of 3 over 2 would give us this angle here between negative pi over 2 and pi over 2. And this is, in our picture, this should be a 30, 60, 90 triangle. Right, that long side of that 30, 60, 90 triangle is negative square root of 3 over 2. So here, this triangle is a 30, 60, 90 triangle, and we're looking at the 60-degree angle, but in the clockwise direction away from our x-axis. So this is equal to negative pi over 3, right? This is the angle that does the job between negative pi over 2 and pi over 2. Now what about sine inverse of the square root of 2 over 2? Well, we could apply the same idea. We're looking for a y, or we have a y value of the square root of 2 over 2. And we're looking for the angle that falls between negative pi over 2 and pi over 2. And that's this angle here. And so what angle gives us a y coordinate of the square root of 2 over 2? This would be pi over 4 if we're just looking for an angle between negative pi over 2 to pi over 2. Of course, there are other angles that give us a y coordinate of the square root of 2 over 2, but we're just looking at angles between negative pi over 2 and pi over 2 for the sine inverse function to be defined to be truly a function for our sine function. So this is equal to pi over 4. Now what about pi? What if we tried to ask, what's sine inverse of pi? Well here, again, the inputs of our sine function, they represent y coordinates on the unit circle, and this value of pi, this is 3.1415, so on and so on. And so this is like asking, our unit circle it's a circle of radius 1. It's like asking us, what angle gives us a y coordinate of 3.141592, so on? What angle gives us a y coordinate up here? Well, there's no angle that's going to give us a y coordinate of anything greater than 1 on our unit circle, because we're looking at a unit circle, a circle of radius 1. It's not going to have a y coordinate of anything bigger than 1. And so actually, this is undefined. This you might say, does not exist. So here are a few more examples. Let me ask you to pause the video and try these examples yourself first, and then we can go over them together. So here is sine inverse of 1. Here we have a y coordinate of 1 on our unit circle. What angle gives us a y coordinate of 1, and specifically what angle between negative pi over 2 and pi over 2. And so here is a y coordinate of 1 on our unit circle, and that happens at an angle of pi over 2. Of course, it also happens at an angle of 5 pi over 2, but sine inverse is just giving us back angles between negative pi over 2 and pi over 2. And so pi over 2 is what we're going to get back. What about sine inverse of 2? Well, this is a lot like our previous problem on the last page. when we asked what was sine inverse of pi. Right here, sine inverse of 2, well, there's no angle that's going to give us a y value of 2 on the unit circle. So here, this is also something that's undefined, does not exist, does not have a reasonable output. And so here, maybe this might be a good moment to bring up the domain and the range of the sine inverse function. So the domain of the sine function we said that it was all real numbers, negative infinity to positive infinity. And we said that the range, well, the set of y values we can get from our unit circle, that's from -1 to 1. And for our sine inverse function, well, the idea is that we restricted this domain of our sine function to just -pi/2 to pi/2 to define our sine inverse function. And so here, the sine inverse is going to reverse the roles of the domain and the range, but it's going to reverse the roles of this restricted sine function. And so the range, the things we can possibly get out from our sine inverse function, they're -pi/2 to pi/2, like we've been saying. And the domain, we can only plug in values between -1 and 1 for a reasonable output for this sine inverse function. And so here, I think this next example is a great illustration of the fact that sine inverse is really only the inverse function to sine on this particular interval. Right, so here, we see sine inverse of sine of 4π/3, and we might expect that sine and sine inverse would undo each other and just give us back 4π/3. But that's not the case here. So if we take sine of 4π/3, so 4π/3, that's down here on the unit circle. We've got this 30, 60, 90 triangle, and sine is going to give us the y coordinate, -√3/2. And so this is the same as sine inverse of -√3/2. But this was one of the first problems we did with the sine inverse function. So if we look at sine inverse of -√3/2, that's asking us what angle gives us a y coordinate of the -√3/2. But again, it's only giving us back coordinates or angles between -pi/2 and pi/2. And so we're going to get this angle out here. We saw that the angle we get back is actually -pi/3. And so we don't get 4π/3, we actually get back -pi/3 because the sine inverse function is only giving us angles between -pi/2 and pi/2. And so one last thing I'd like you to be aware of is that sometimes the inverse sine function y is equal to sine inverse of x is also given the name arc cosine. Y is equal, or sorry, not arc cosine, arc sine. Y is equal to arc sine of x. So here, these are two different ways of writing the same thing. And so in all of the previous computations, I could have replaced sine inverse with arc sine of x, and that really would have been communicating the same problem, the same idea. So, we might say something like, what's arc sine of -√2/2? And in this case, that would be -pi/4. So just a different way of saying the same thing.